Andres. I work for Citus Data, and fortunately I get to play with Postgres for most of my time, either normal core Postgres or Citus's extensions to Postgres. And I'm going to talk about the buffer manager, which is the component that deals with I/O in most of the paths of Postgres. And I'm going to explain what it actually does and how it works, and then mostly focus on where it doesn't actually work that well, and where we can, what we need to do, or which areas I see where we need to improve it. And I think I'm going from the point where I say I have a good idea what we want to do, and to the end where I say I have no clue. So I hope to get to it later. So to get a basic understanding, you have to know that Postgres uses a process-based model, which means it doesn't use threads internally. It has, for each connection, it has a separate process, and there's a bunch of internal processes that do some things, and all of them are connected using shared memory. That's this side, and in that shared memory we have sub areas that are responsible for different parts. Then there's some other parts of this, when you do a query, that are done in the process local memory. So if you sort the data, that happens. Sorting happens in each process, in each connection itself. So we're mostly going to focus on the shared memory side, and we're mostly going to focus on the buffer cache. So what is the buffer cache actually? It's a structure where we try to store data so we don't have to repeatedly ask the disk to do I/O. So it's basically organized by having a buffer mapping hash table, which says, okay, I want to look up the page, read the page 15 of that table. Then it says, okay, we have that stored somewhere, or it says, I don't know about the page, you have to read it from disk. So if you want to read data, that basically works in this way. When we first ask the hash table where would in the hash table the entry reside that for the specific page of the specific table that we want to read, and in this case it's in this position, and there's no error from here, so there's currently we haven't stored it anywhere. So what we do then is we find a free page, and the process of how we find a free page I'll explain in this later step, and then say, okay, I now can use this page to store the data, and say, I have to lock the page. I have to set the tag, and the tag is the identity basically of that buffer cache page, and that says I'm the page 15 of the table so-and-so in the database so-and-so. And there's some other things that I'm going to come to later. So I do these, and then I ask the operating system, can you please, I'm opening a file, then I say, read these bytes from the file, and then the OS doesn't actually necessarily read the data directly from disk. It might also have that data cached, because we don't use this a mode where we ask the OS to never cache data for us. And if the OS hasn't cached it either, the OS asks the storage, and the storage tells it the OS, and then the OS tells us that it has this data. And unfortunately, that's hard to see on this, the red here, sorry. This here says counts. And every time we want to read a page, but it's already cached, we increment the count of the page. Why? I'll explain later. So, and if we want to write to a page in the database, we don't actually have to go to the OS. What we do is we set the lock, that says lock, we set the lock, and we set a flag that this page is dirty, and then we just modify the data. And then we are pretty much done with the modification. We don't always directly write back data to the disk or to the operating system. And that's important, because if you were to do like a couple hundred inserts into a table and you expect them to all fit into one page of the table, doing a write to the OS every time would be pretty expensive. It would also have the problem that if we had not enough control over when we crash which data is on disk, so we couldn't be durable. But that's comes later. So I said earlier that sometimes we need a new page, a free page where we store data if it's not currently cached. So the way we do this is we use the so-called clock sweep algorithm. We just organize all these pages that I had earlier here. Here we have 0, 1, 2, 3, 4, and normally you have obviously a cache that's bigger than just 4 pages. So we just organize it as a ring, and we start at some position where our clock hand is, in this case 2, and then we check whether is there currently a page, valid page at that position, and then we check, if there is, we check which usage count has it. If it has a usage count of 0, then we immediately can reuse it. If it's not, we just say, okay, I'm decrementing the usage count by 1, and I go to the next page. And then I do the same until I find finally a page that's either unused entirely, in which case I can directly use it, or that is currently has a usage count of 0. If then I'm done with that clock sweep. And which means that I have to go around here until I find one of these pages. And obviously, if I found the page here, the number 4, and I detected it has still this dirty bit set that we earlier said, that means we have to write it out to the operating system. And the way that works is we, again, just get the log and say the operating system, please write back the data. And the OS writes back that data into the page cache. Again, we don't use any flags that tell the operating system to directly write it to disk. Instead, it just gets written to the OS's equivalent of the buffer cache, which is also often good, but also sometimes problematic. And there's one additional important component to understand the performance of I/O and Postgres, and that's called checkpoints. Postgres uses a so-called write-ahead lock for crash safety, which means whenever we do modify the data tables in Postgres or indexes or anything, we first write it into a separate log, and where it says, we are now going to modify the table at that position and do something. And if you crash, we just read that log and redo everything. But, so this is the log, we store those in small sequential files, and if we crash, we just start at the beginning and read all the logs and replay them. And that's a pretty standard crash safety technique used in several database systems. It's nothing really Postgres specific. Obviously, how exactly we do it is Postgres specific, but in general, it's not. And every now and then we need to get rid of the old logs. If we never said something, if we never got rid of the old logs, if we crashed, we would need to replay all the logs since the creation of the database. And if you imagine a database that has been created 10 years ago and has gotten thousands of updates every second since then, that would take basically forever. So every now and then what we have to do is we have to create a so-called checkpoint, which means if we create a checkpoint, we can remove all the logs that were created before that, and if we crash, we then can not just start from the beginning, but from the point where we created the checkpoint. And these checkpoints basically require that we go through the whole shared buffers that hold all the potentially thousands to millions of pages, and go through all of them and see which ones are currently dirty. And all the dirty pages have to be written out to disk. And if you have a shared buffer setting of, say, 500 gigabytes or something, that obviously can take a while. So we don't actually perform those as fast as we can, but we spread them out over time. So we write at a steady rate, or we try to write at a steady rate. And if we're done with that, writing out all the dirty buffers, we say fsync to all the data files, so these changes are guaranteed to disk, and after that we're pretty much done with the checkpoint. The details there are a lot more complicated, but that's basically it. So to explain why I'm actually bothering with all this, if you use an untuned Postgres and run our Postgres benchmark tool against it. In this case, the database is about 20 gigabytes large, and this is the standard settings of Postgres, which are aimed towards a very low memory system, so maybe not appropriate to run against a 20 gigabyte database, but you can see that with the standard settings we get short amounts of okay speed, it's pretty good speed, and then it tanks for a long while, and then up again, down again, up again, down again. And that's for various reasons. Most importantly, the shared buffer setting by default is something, I think 48 megabytes, might be 64 megabytes. So we constantly are busy writing all the, whenever we want a new page in the shared buffers, we have to write out old data first, and then there's also a setting that says how long can checkpoints take, and how much data might be stored on disk before we start the new next checkpoint, and that by default is 48 megabytes as well. So those are not really suitable for a big system. So let's, even if we tune that, set shared buffers to something, we can see now, okay, the good performance lasts a couple seconds longer, but not very much. But if we set shared buffers and the maximum size of the checkpoint to something large, we can see that most of the time we have fairly good performance. It's important to notice that we now have a different scale here, because this one was in total 300 seconds, and we are now at 3,000 seconds, because the first 300 seconds are actually all good performance. And that's because by default, in the first 300 seconds, we don't start any checkpoints. So, but you see after that, we have a very up and down movement in the actual throughput, and the red line, which looks brown black here, is the latency. So we can see that every now and then we have latency spikes where individual queries take 500 milliseconds, 600 milliseconds, and up and down. Obviously, that's not something you want from a database that's used in production. Who of you have ever seen such spiky performance in Postgres? Okay, that's a fair number of people. Cool. So the question is then, why does this actually happen? And you can actually in Linux graph how much dirty data there's in the kernel, how often we wrote something to the OS and said, hey, please kernel, write this as fast as possible. Then the kernel only writes it back into its page cache, and we are continuing. And you can see that every now and then we have huge spikes where we have a lot of dirty data. I think this one is blue supposedly, and this one is red supposedly. And the blue ones are the dirty data in the kernel, and the red one is then how much data the kernel is currently trying to write back. So you can, if this were easily viewable, you could see that first the dirty data is high, and then suddenly everything goes into write back, which means the kernel tries to write back that data as fast as it possibly can. And if the kernel is busy writing data back as fast as it can, other I/O is very slow. For example, we have to write to the val, we have to read data from disk because it's not in memory. All that is suddenly very slow because the drives are fully busy doing something else. That's especially bad if you have like rotational disks, but it's also still, even if you with SSDs, you can see the same problem. And this is actually not that bad example. I've managed on rotating media to get stalls over 700 seconds where not a single transaction could happen, because the kernel decided to buffer 7 gigabytes of data and it was all random, and then rotating media writing back 7 gigabytes of random data takes a long while. So an easy idea would be to say, please kernel, don't cache as much dirty data. So what you can actually do, in Linux, I don't really know about other operating systems, I'm sorry. There's 3 tunables that have an influence here. You can say, like, that's the most important ones. You can say dirty bytes and dirty ratio. And they say, after that dirty byte or dirty ratio of the total memory is reached, don't accept any more writes, block when somebody tries to write. You can also set dirty background bytes, and that's or dirty background ratio. I always would suggest tuning the ratio, the number of bytes, because sometimes you might decide to add another 500 gigabytes or something like that memory, and suddenly your kernel decides to cache much more data, dirty data, which then causes much more big slowdowns. I've seen that a number of times. And dirty background byte says, after that many bytes are reached, trigger the kernel internal mechanism that does the write back. So what I decided to do, let's just experiment setting the background to 10 megabytes and the dirty bytes to 20 megabytes. So that's really, really small settings. And if you then do that, this is again zoomed into 300 seconds in the middle somewhere, you get the slowdowns are there for a very short amount of time, but most of the time, that's when no checkpoint is happening, and that's when the checkpoint is happening. The performance is pretty good. So with that kind of trick, you can get pretty good performance. But on the other hand, the kernel doesn't do this dirty data caching for no reason, and we basically told it to write back everything to disk immediately. And for example, if you also had on the same database a query that required an on-disk sort, it suddenly would do much, much more disk I/O. So it's not really suitable to, not even on a pure database system, to tune it that way. You can get away with it if you have a pure OLTP system, and you can actually, in those cases, it might be a good idea, but generally it's not something that we want to do a system-wide setting that says, don't ever cache any writes for long. So the goal basically was to get something in the vicinity of this kind of performance without having to change the system-wide settings. So the Fabian Coelho, I don't really know whether I pronounced that name right, and I worked for a while on various versions of patches that basically said every now and then we try to force the kernel to write the data back now, but we do it in small enough increments that there's not a huge spike in I/O, because then that would have the same problem. So in Linux has luckily the system called sync file range, which unfortunately is littered with comments don't ever use. The man page actually contains this sentence, not verbatim, but pretty much, and this has no guarantees that are documented. Okay, but it works well enough, and we don't actually use it for durability. We just use the syscall to say, please write back the data now. We still do an fsync whenever we want it for durability. This is it's not a safety critical mechanism. The only thing we don't want it to do is to crash the system or so. And that it actually does. On other systems, we can use the msync syscall to force the kernel to write back data. That works, for example, on FreeBSD pretty well. On Linux, it doesn't actually work, but since we have the certain file range call there, that's pretty helpful. So what you can do is to use these sys calls whenever we have dirty data, say more than a megabyte, we've written more than a megabyte, then we say the kernel, please write back the data now. And we have to do that in the checkpoint, we have to do it in other internal processes, so for example in the background writer, and what's actually pretty important, we also have to do it in the backends that process the actual queries, because they might actually doing this clock sweep and then have to write out dirty data. In those cases, they can actually be the biggest producer of dirty data in the kernel. So, but the problem is that if you immediately do sync file range whenever there's dirty data, that can actually lead to a lot of random I/O, because there's no specific order in which the buffers are ordered in shared buffers. That most of the time that's pretty random. So if you just have in the check pointer go over all the buffers and write them out in the order they were in memory, then you get a lot of random I/O. That is kind of somewhat okay on SSDs. It hurts there as well, but it really, really hurts badly on rotating media, and people still use that. So the idea there is for the check pointer, which has to go through all the buffers, we first go through all the buffers, remember which ones are dirty, and then after sort them, and then only write the sorted buffers out. That is a bit of overhead, like doing the computation, but it's not that much. So that actually helps a lot, and those two together then give performance that looks like this. So we are slightly lower than the one where we set the kernel settings to pretty much no dirty data caching, but we're not as bad as before. It's worthwhile to note that this pgbench benchmark, what it tries to do is as many transactions per second as possible. And obviously that will always reach the point where something is the bottleneck. And if you construct a system where I/O is the bottleneck, by choosing the right settings, you'll always have slowdowns at some point. If you, for example, like here, start the checkpoint, there has to be some slowdown. I think if you use a newer kernel, 4.4, that line here is about here, because there was actually a kernel, not a bug really, but a misoptimization in the sync file range syscall, which explains the difference between here and here. So the line is actually, if you use a very new kernel, the lines are here, the same. And this one is the version with this forced flushing. So I think that's pretty good, especially because an unpatched version has both much higher average latency and lower throughput in total. So we improved on both sides. So I think that's pretty good. So now we can get into the area where I'm saying we have less good solutions, where I think we might have something, but I think we're pretty much experimenting at this point. One of the problems is that this buffer mapping table that I talked about earlier, the lookup in there is not free. It costs a lot, actually. If you do benchmarks where you touch a lot of pages in memory, which are, you do it from a lot of processes at the same time, most of the time is actually spent in the buffer, our hash table implementation. And partially that's because our hash table implementation isn't that good. It's showing its age in some parts. But the bigger part is actually because our key for the hash table is, in this case, is 20 bytes. I'm going to show why this wide. And every time you looked up the key in the hash table, at some point you need to verify that you didn't have a hash collision. And then we need to recheck the key, and that's actually where we spend most of the time in my experiments. This also has the problem that a hash table isn't actually very cache efficient. You have a good worst case average case behavior, but because if you look up two neighboring pages, they're going to be in two totally different parts of the hash table. And modern CPUs are fast as long as you have hit the CPU cache. But as soon as you hit the memory, that takes a lot longer. So I did actual experiments about how long it takes the pure lookup into the hash table. On average takes, on a loaded two-socket system, we spend the pure hash table lookup, we spend 1,800 cycles each and every lookup. That's the average. Obviously, some are much faster, some much more slower, but that's not really fast. This also has the problem that pretty much by definition, a hash table doesn't have a meaningful ordering. It would be very nice if we didn't have to sort the buffers to do the sorted checkpoint. And more importantly, it would be very nice that if you were deciding we need to write out one dirty page, we would say, are any of the neighboring page in the file also dirty, and write them out at once, because that saves I/O ops on the disk device, and it saves us the syscall. Unfortunately, that's at the moment we would need to do new lookups in the hash table to both sides, increasingly large, and that's pretty expensive with the hash table. So we would like to have a data structure that's both has ordering and has cheaper average time lookups. Because one other problem with the current hash table approach is that if you do, for example, a drop table and you have a very large shared buffer setting, what we need to do is we need to go through the whole shared buffers and look, do we have anything for that table cached, and then remove it from shared buffers before we can drop the table. And if you, for example, have a regression test suite which creates thousands of tables in a very short amount of time, and then drops them again and does the same again, you suddenly have the weird situation that if you have larger shared buffers, the test takes much longer. Not very intuitive, in my opinion. So the buffer tag, which is the bit we use to identify buffers, currently is consisting of these three. We know which table space the data is in. We need to know which table space it is. in, we need to know which database it is in, and we need to know which relation it is in. The relation here can be an index, it can be the table itself, it's the table, so something like that. And we need to know the fork number. The fork number is where we store additional information about a table. For example, where there's free space in the table, or something like that. And then the most important part for the purpose of the buffer cache, we need to know which block the table is in. And each of these pretty much are 4 byte long, and so we arrive at a 20 byte key. And that's actually, comparing 20 bytes at every cache hit takes a lot of time. We can optimize from the current code to something doing larger comparisons at once using different instructions, but that only gives us a little bit. So what I'm thinking that we should do is use a so-called radix tree, or a specific variant of a radix tree that I think Linux mostly popularized. And that basically works by dividing the key, in this case I'm assuming the key is 4 bytes wide, into like parts into prefixes. So we have 6-byte prefix in this example and a 6-byte prefix, and then the last one, because we only have 32 bits, is 2-byte bits wide. So the way that these prefix radix trees work is that on every tree level you have, for example, here in 6-byte, so 2 to the power of 6 entries, and then you just convert the first 6 byte into an offset into the tree levels, tree nodes table, and say if it's, for example, 17, the first bits are 0 and then 17, and you look up into the 17th slot, or into the 18th, because you're 0 next slot. Yeah. And from there we just then have the location of the next level, and there we look at the next 6 bits, and then at the next 6 bits, and so on. And if your tree is not too deep, that actually is a pretty good data structure, because for modern pipelining CPUs, that they actually can do the next lookup while the old lookup is still processing. So you end up with such a tree, and then in the last level, you don't store pointers to the next level of the tree, because there's no next level. You say, okay, this entry is at in the buffer 1. This should be a B, sorry. In buffer 1, or in buffer 999, or something like that. And the problem is that I said here that we had for 32-bit with a 6-bit wide per tree level, we already need 2 to the power of 6 array entries on each node. So we can either, to have a wider key, we can either say store more entries per node, which means that our space overhead increases, or we can say we have more node level, which increases the lookup time. So it would actually also here be desirable to have smaller keys. My first approach was to say, let's try to get rid of individual parts of our hash lookup key, because we don't necessarily actually need all of them. We could relatively easily get rid of fork number, and stuff like that. We could relatively easily actually get rid of the table space for the purpose of the lookup in the hash table. But it's all pretty tricky, large amount of work, and it doesn't. We still have, at the very least, the database node, the relation node, and the block number. So the next thought was, why do we actually want only one tree that stores all that data? We can have basically a tree of trees where we store the table space, database, rel file node, and the fork in the upper level of the tree, and then have a second level of the tree where we only key by the block number. And that's the one where we will be doing very frequent lookups. I played around with 2 different ideas, one where we say we have a tree of trees, and then in the middle we have a tree where it says access to the relation, and that's actually a separate tree, and that points somewhere else. That has the advantage that we can store in this intermediate tree, we can store information about each relation. For example, we can store the actual size of a table. Currently, we don't actually know how large a table is before doing a file system call. If you constantly do, for example, select star from table without a predicate, what we do is we do an lseek seek end on the table every time to know how large it currently is. That actually has some cost. On older Linuxes, that actually you could actually see like that we spend most of the time in the lseek system call because it had the locking problem. They fixed that now, but still it's not nice to constantly look up the size, which probably didn't change. So it would be nice if we were able to store that in memory. The easier solution, which I was using mostly for prototyping so far, we have this in-memory notion of basically a relation file handle where we have the kernel file handle stored and stuff like that. And we could basically use a cache lookup pointer into the larger tree, which stores the whole thing, and just jump into the larger tree and check, is this still the page the node of the tree that I thought it would be, which needs some overhead, but it's possible, and then if it's not, just do the lookup from the top again. I've played around with both. I'm not yet sure which one is the better approach, or we might also convert between the both. There is some problems with using an approach like this, because if you have a very sparse lookup filled shared buffers where you only store the last page of very, very many relations in a database, all your trees need to be very deep, then you can possibly need a lot of memory to do this. And at the moment, if you ever ran into situations, my prototype just says, okay, I don't have the memory for this. That's obviously not something we want to do for real. So we have to do some smarts there. I think that's a reasonable approach. I'm not sure whether it actually will work out fully in practice. Early benchmarks will say it solved the problem of the expensive lookups, then the next bottleneck shows up as usual. So I managed to find this experiment to do like 20% in a large number of use cases. After that, we just hit another bottleneck. So I think this might work, this might not. I have the hope of submitting a patch early in the 9.7 cycle, because I don't think there's any way I can do this for 9.6, but we'll see. So this was the one where I think this might work, and now we come to the ones where, whatever, I have no idea. So the problem is that this clock sweep that I showed, where the clock goes around, generally doesn't actually scale very well. The first problem was that we used a single lock protecting the clock sweep for a while, and if you had a high cache replacement rate, that lock was very, very heavily contended. We now have a lock, basically an atomic variable that says the clock hand is there, and that has better behavior. But the real problem is that because we have this usage count, which basically emulates an LRU, we have to potentially go to find a replacement buffer, we have to go around the whole clock 5 times, because that's the maximum usage count, to find a replacement buffer. And if you have 500,000 buffers or something, that takes a while. And if you have a lot of processes that do that at the same time, that doesn't scale very well. So we really have the problem that the current approach isn't very scalable, and that's pretty much a fundamental issue of the algorithm. There's not much we can do about it. So, and the worst case really is if you have many lookups in the hash table, more than you have cache replacements on, because then you always have basically a usage count of 5 on average, and you always need 5 cycles around the clock to drive all the buffers to 0 and then replace one, which has 2 big problems. A, it's super expensive to do, and B, it means that we lose all the information about the frequency of access that we actually wanted to do with the LRU approximation, because we set it all off switching between 5 and 0. So we have no idea. Essentially what we did there, in many cases, we have a very complex implementation of a random replacement algorithm for cache replacement. We might want to go there, but then we should do it in a cheap way. So I think there's some algorithms that we can try. I wish you would some people helping with this. It's a hard problem. It's also, there's some issues around patents and whatever, and it's hard. So, and the last problem I think we have, which can be pretty big, is that I said earlier we use the kernel's page cache. And the kernel page cache often will store, because we write data there and then the kernel writes it back, but it will keep the clean page in memory. And if we read data from the kernel, we also hit the page cache first and then read it into our buffer. So you often end up with a situation where a page is both in our internal cache and in the operating system's cache. And that's obviously not a very efficient way to use memory. If your entire database fits into shared buffers, that's not a problem because the kernel will see these pages are never accessed. But if you have this database system which doesn't fit into the operating system memory or in Postgres page cache, then you have the problem that we waste memory storing the most frequently used information in both caches, but all the other ones we don't store anywhere. So pretty much the only realistic way to address this is to completely avoid the kernel's page cache and use this so-called O-direct mode, which basically asks the kernel to ask the hardware directly without going through the page cache to fetch the data. There's a lot of problems around this. For one, how to use O-direct efficiently varies widely between the operating systems. And for another, you need to, there's a lot of performance work the kernel does, or tries to do at least, and where it uses the page cache for, which we would have to all fully emulate. The only reason we got away with writing back data unsorted in many cases was and how we get away today with writing 8 kilobyte blocks individually with separate system calls is that the kernel merges those requests in a lot of cases, which helps the hardware to do less I/O logs. So we would need to do all of that ourselves. It's also, which I think is the biggest problem, it's not very adaptive. At the moment you can set shared buffers to 1 gigabyte, and as long as there's enough memory, you can still deal very well with a 10 gigabyte database if you have enough memory, because the operating system basically acts as a transparent extension of the shared buffers. But if we don't have that anymore, we need to, it becomes much more important to tune shared buffers correctly. And at the moment, you can change shared buffers without restarting the database. To me at least, it sounds very hard to change that, given the way it works internally. And so I think even if we offer that as an option, it will not something we can switch on by default, and it will not be usable for everyone. So it would be very nice if we had a more close control over the kernel's page cache. It would be very nice, for example, if we could say, we are evicting a page. Hey kernel, would you please update your page cache with the current state we just had in memory? But I talked to a bunch of kernel developers and they were slightly hesitant about that idea, which I kind of understand, because they would need to trust us that we just gave them the right content of that page. So, I don't know. Yeah, I think those are the big problems that I see around I/O and Postgres. Any questions? We have a microphone. Okay, just ask it and I will repeat it.
I'll speak louder. So it's not mmap then, because if you're mmap, you're working directly in kernel's page cache, right?
We can directly use. So the question was whether we are using mmap and whether we could just avoid using the double buffering that way. And no, we can't, because for durability reasons, we need to ensure that the val hits the disks before the buffered contents. So there's an ordering constraint between the val and the buffer cache. And that's basically, I don't think there's really any way to get around having a separate buffer cache that is not kernel controlled. I don't, at least, we could play around with mlock, but that doesn't really work that well. So I don't see that as possible. Yeah, so I don't think that's really possible. Would be nice though. Other questions?
I've got another one.
let's ask Kevin first.
I was surprised to see that you recommended reducing the dirty ratio or dirty bytes, not just the background one, because in my tests I got the best by having it start the writing in the background at a very early point, but setting the threshold where it holds up I/O to like 40%.
Okay, interesting. My experience was that if you set the dirty ratio to something very high, it avoids stalls for a longer while, but when you then do a checkpoint, which does an F-sync, you get enormous stalls.
Well, yeah, but
So-
the trick was tuning everything else so that you didn't get that. I mean, it was complicated to do.
So yeah, I think that is really heavily workload dependent and how high your rate of redirting it basically is. I think I don't really want to spend too much time hand tuning it because I don't think it's really a suitable approach for anything but a workaround. So
I get that. I was just a little surprised. And
Yeah.
had to ask about it.
okay.
Any more questions? We're recording this, so please use the microphone. First here.
I'm not sure if I got it correct, but I think you said the usage count of a page is reset after 5. Is there any?
No, it's
specific
limited to
reason?
5.
Yeah, is there any?
So the reason for
specific
that is that if we were allowed to go up endlessly, we would have to go around the clock as many times as the highest number, and that would be potentially the new maximum number. And it's just basically a trade-off between accuracy and between the speed of finding a new buffer. So you can, it's a define, I think, in the PG config manual file, so you can recompile Postgres with a different setting. But I think we need a algorithmically better approach, not that. If we had a better algorithm, we definitely would want to increase the accuracy of usage information.
So if you decouple the aging of the pages from the scanning, could a scan then just remember the best page it found?
Skipping through the swaps instead of going sequentially.
You do one sweep.
And so
I don't know if this is possible.
we basically have, what I experimented with, or basically have code for, is a background writer that does the whole clock sweep and then puts all the free and clean buffers into a list which is just use this buffer next. So
That would work too. That's basically a free list. Isn't it?
yeah. So I did that, but that still means you have to touch every buffer in that separate process somewhere.
Yes,
I'm not entirely sure
I
how.
was thinking of something along the lines of vacuum, where the age field on a page goes up to 16 bits or something, and they keep going up and up and up, and the sweep just does one sweep, remembers the best page it found,
Okay.
and once in a while this vacuum comes in and goes, oh, these numbers are about to overflow.
The problem is that at the moment we can do in lots of workloads like 100 to 10,000 clock sweeps a second. So storing the recency information like somewhere else would have to update very fast. I mean, you can have workloads where even if with gigabytes of shared memory, you have buffers that are only most of the buffers only stay there for fractions of a second. But it'd be interesting. Let's talk later.
Would you segmentally sweep the buffer?
Yes, that's what I think we might end up doing. I don't know, but yes, I think a segmented clock sweep OU might be an approach where we move data. Yes. Other questions?
Sorry.
Hello. Do you have any simulation data like access traces to experiment with different eviction algorithms?
Yes. I was asked to post that earlier. What I did was basically use perf and custom probe to create trace points that emitted and then log that to a file, and then wrote a tool to basically emulate what the Postgres cache replacement does, or by hacking up Postgres to do that for me. And I think that's one part. The problem is that doesn't really, in that algorithm we don't necessarily come up that bad with that algorithm, because with you simulate cache accuracy or cached ratios, you don't simulate the cost of doing the caching. At least not that easily. Because there's like, a lot of it is the cache misses that play a huge role. Because if you touch all the shared buffer headers, and you do that on all CPUs, so that's on a system with several sockets, that's really a lot of inter-node traffic. So that's it gets very hard to simulate that accurately. But I think for the raw algorithm, we can do a lot with that. Great.
Any more questions?
My screensaver.
Here's one question.
Hi.
I have one question. Very interested to see how the internals of it all works. But I was looking before this presentation on the online guidelines for a standard VBA, how to tune buffer cache, and it's very complicated.
Yes.
And there seems to be a gap in the documentation and a certain amount of disagreement even within the official guidelines from Postgres about whether it's something to 40% of the RAM but you super server with terabytes of RAM. You don't want to push your shared buffers to 400 gig.
I mean, I've seen good results with shared buffer set to over a terabyte. I've seen terrible results with it's being set to 50 gigabytes because it was too high. The problem is that it's so highly workload dependent that it's very hard to give a tuning guide that's shorter than a full 45-minute presentation.
Is there anywhere online you can have that or other presentations? I'm very curious about it.
I made this presentation out of one where I had some of that advice. I think the problem is that there's different optimization strategies. You can say, I'm optimizing for using the kernel page cache and setting it low. I'm not aware of any good, fully written out documentation on the topic, unfortunately. I think that's very sad. And I think a lot of the information out there is pretty wrong. But yeah, maybe we should improve on that. Sorry, I don't have a better answer.
Any more questions? Okay, hold on.
Do you have any concerns about adding overhead support, making that harder and adding another dimension to tuning that when we're already struggling to communicate users there?
I mean, if you add ODirect, the advice basically is set shared buffers as high as you possibly can.
So it actually simplifies.
In a way, yes. But on the other hand, it gets more important to tune like OS, and will be the differences between the operating systems will be getting larger. So, and we might end up with tunings like we probably need multiple background writers and multiple other processes that do the stuff in parallel to get because we have several I/O channels on modern hardware. So that tuning, we don't know what tuning we actually need. So it's a bit hard to predict that, at least for me.
Any more? Sorry. You still got some slides, or you still got some slides?
I have my beginning slides. So yes, that's it.
No more questions? Yes, here.
If you look into maybe splay trees or something, like a auto balance and like most access nodes on top, and maybe do a double one, so you have a separate one for the
I've thought about that. The problem is that the locking gets very hairy. I mean, you can do a radix tree lock free. I can't even think about how to do a splay tree in that way. So that's one of the part of the reason. And the other part is that this you can it ends up being rather simple loops, and they end up being relatively easy to pipeline for the CPU. And I don't think that you can do that as easily with a splay tree. But please experiment with it.
All right, I think that wraps it up. Thanks Thanks, Andres. The next talk will be about JSON by example.